All right, so today we basically just finished the theory. So today we're just gonna do like a short recap, and I was planning on doing more separable differential equations, and then for the last hour, probably actually some problems from the past exams. That's my plan to show you how it works. And yeah, that would end my teaching part, and you're gonna start with Niels next week. But I'm just gonna give like a short recap of separable differential equations. Literally all that I wrote, all that I will be writing now is I wrote last time. So just a short recap on separable. Oh yeah, of course. That should help as well. You didn't miss much. I just wrote the title. Again, I'm just gonna rewrite the theory pretty fast. The whole idea was basically having this differential equation that looks like this: f of t g of x. Basically, the whole idea is that you could split the right hand sides into only x, only t. After this, the next step, which you had to do, was look for constant solution, which is just a fancy term for putting g of x is equal to 0 and getting x is equal to something. Then, once you've looked at a case g of x is equal to 0, I am just gonna write what you have to solve. You just got to solve integral of 1 over gx dx equals integral f of t d of t. And once you solve this, you should get an answer eventually, x being equal to x of t being equal to something. Okay, that's the main idea. And don't forget, whenever they're asking for the general solution, you got to present both of these. Okay, that's the main idea. Now, if there are no questions on the theory, and on this short reminder, I'm just going to give an example, and I guess we're going to start doing some problems, see how it works. So the first one I'm thinking of is x dot is equal to e t plus x. Okay, that's the first one that I'm thinking of. Now, as I said, the first step is always identifying and trying to make your function look as much as the function you've learned, which is x dot is equal to f of t times gx. And you just got to make it look nice or look as close as possible. In this case, written like this, the function, I can't really do much. So the idea is to just write like this times e of x, right? When I'm multiplying powers, I'm just adding their exponent up. So my idea is to just split it so I can identify g of x and f of t. All right. Now that we've done that, the next step is, oops, ouch. I'm just gonna look for a constant solution. So basically, I'm just gonna check g of x is equal to 0, which means e of x is equal to 0. And this is impossible. There's no solution in this case, right? No solution for x. So now that we're done with this, we can just move on to the next step, which is just computing one this thing. Now, if on the exam for some reason you want me to show the proof of why you need to compute this, sure. Does it matter? Absolutely not. Okay. Realistically, I am very bad at remembering formula, so I just derive everything on the spot. But if you actually can remember stuff, which I can't, I would highly recommend just remembering this and not bothering with computing it on the spot. Anyway, I'm just going to replace this g of x with e to the x from my initial identification, and this is e to the t, right? This is how it looked from here. F of t was equal to e of t, and g of x was equal to e of x. So now I'm just going to plug them in, and I get integral 1 over ex dx is equal to integral et dt. Now, this is e to the minus x dx, and this is just e to the t plus a constant. So this is minus e to the minus x is equal to e t plus a constant. Now you gotta take an ln, which is probably gonna mess a lot of people up right now, because well, first of all, put a minus because this is something's wrong here. But e to the minus x is equal to minus e of t plus a constant. And now I take the log here, the ln, log ln. And the whole idea is that I get minus x from, or let me write it in steps actually. So the main mistake that you will do here, which I'm trying to correct, is basically, oh wait, there's no minus, et plus constant, is when you take the ln, you're gonna write ln of e minus x equals ln of minus et plus ln of c. This is wrong, bad. Right? ln doesn't work that way. When you take ln, you take ln of the whole thing. So the solution is ln e minus x is equal to ln of e minus t plus the c inside the ln. Okay, the same as the exponential, works the same way. Or if I had, let me give you an example. If I had 3 is equal to 2 plus 1, then when you take an exponent or take an ln, it's the same thing. This is equal to e to the power of 3, e to the power of 2 plus 1, not e to the 3 is equal to e to the 2 plus e to the 1. If you don't believe me, you can try the right-hand side. The math just doesn't work out. But just to be done with our initial problem, this is minus x of t is equal to ln of e minus t plus a constant. I think there's a minus here, which I missed. And so xt is just minus ln minus et plus a constant. And that's kind of all you have to do if they're asking for the general solution. Now, if they continue the problem, they're asking you questions like, if they're asking questions like, find particular solution such that x of 1 is equal to, let me make the math look nice, minus ln of 10. If they're giving you such a problem, they're basically asking you to take the general solution and plug in t is equal to 1 and x is equal to minus ln of 10. So my equation is basically just minus ln of 10 is equal to minus ln minus e to the power of 1 plus a constant. All right, I replaced my x with minus ln of 10, and I replaced my t with 1. So, and now all I have to do is solve for the constant. The constant is basically what's going to give me the particular solution. Now, minus minus plus, ln just gets removed, so I get 10 is equal to minus e plus a constant. So the constant is 10 plus e. And at this point, it's over. If you want to be a nice person, I guess, and make it easier on the grader, especially if you're comfortable that you did the correct thing. This is something else. If you're comfortable that you did the right thing, you can just say x of t is equal to, and just replace the c. So minus ln minus e of t plus 10 minus c plus c. So basically just replace the constant if you're comfortable that you did everything correct. Because if you do this in most cases than not, the grader is just going to look and be like, yeah, sure, that's the correct answer. Seems like you did the right thing along the way. Okay. Any questions on separable before we go into, I guess, more complicated examples? And again, the only thing that can be complicated in differential equations are just what is this? Are just the integrals that, oops. This wasn't the only thing that can get complicated in differential equations are just these two integrals that you'll have to compute. So when I mean difficult, I just mean we're going to have difficult integrals. The theory is not there. There's not anything like very complicated in terms of, oh, I have to remember that, otherwise I'm not going to solve it. It's purely just a calculus exercise, right? Once you've identified f of t and g of x, it's purely just a computation exercise, which you should be getting quite comfortable with. Now, let's see if we can take a more elevated example, which actually might be from econ. So this is called the logistic growth rate. Okay. And I think, wait, the example is x dot is equal to r times x times 1 minus x over k, where they tell you that r and k are positive numbers. Okay, this is what's called the logistic growth. I've never personally encountered it, but I found it online, and I thought, why not? So the first step that we have to do is just identifying the stuff, right? And in my head, I'm looking for something that looks like f of t times g of x. What's the first observation? There's no t. Since there's no t, I'm already kind of comfortable. I'm expecting this to be very easy, right? Because one of the integrals just isn't there. So let's just see exactly what we're talking. So f of t is equal to 1. There's no t there. And I'm just going to make g of x be equal literally to everything else. Okay. So now, before we move on, I got to take the constant solution. Which is g of x is equal to 0. Rx1 minus x over k is equal to 0. And in this case, either this is 0 or this is 0. So I either have x is equal to 0 or 1 minus x over k is equal to 0. So I have two solutions, x is equal to 0 and x is equal to k. Everyone following what I'm doing? Basically, check the constant solution, check gx. Now comes the ugly part, which is computing integral of 1 over g of x dx is equal to integral of f of t dt. Okay. And now I'm going to help you out in the sense that I'm going to write what g of x is, right? G of x is just this thing that I identified here, which is rx 1 minus x over k dx, integral f of t, that's 1, dt. So this is equal to this t plus a constant. Okay. From here, t plus the constant. Okay, now, since we're a team here, I did half the problem. I did the right-hand side. You guys did the left-hand side. So I'll give you 5 minutes to do the left-hand side. It's only fair. Okay, this might actually be a little bit above your pay grade. So I'll actually help you on this one, and I'll give you the next for you guys. I think this is this method. There's a discussion whether or not it has been taken out of the method of solving this particular one. There's still a discussion if it's off the tables for the course or not, but I think it's a cool method to know. So I'm going to show you the method to solve this one, because if you haven't seen it before, it might be quite rough. So my first step is to take the r in front, the 1 over r. So I get 1 over r is integral from 1 x over k dx. Okay. Now, my next plan is that I hate fractions. I hate stuff that looks like this. 1 over 2 over 3. I hate stuff that looks like this. So I want to get rid of it. So I'm just going to multiply everything with a k. Right? Because I want this k to go away. That's my plan. So I'm going to get integral of k x k times 1 minus x over k dx. So this is just k x, and I'm just gonna multiply this k with both the terms inside. So I get k minus x dx. All right, makes sense to this point. Now, just to make stuff look much obvious, sure, just to make things look much obvious, I'm just gonna write it as minus integral of x minus k. I just changed the sign here, right? From k minus x minus k. That's my only change. And now here comes the cool, I guess, trick theory, which works quite nicely. It goes like this. And I'll give you an example. The trick goes like this. 2 over x x minus 2 is equal to 1 over x minus 2 minus 1 over x. If you don't believe me, just calculate it. All right, let's calculate it together because I see a lot of confused faces. So how do you subtract two fractions? You just bring them to the same denominator, right? Like, so I'm just gonna amplify this thing by x and amplify this thing by x minus 2, right? That's how you compute fractions, right? Like if you have 1 over 2 minus 1 over 3, you just do this times 3, this times 2, so you get 3 over 6 minus 2 over 6, that's 1 over 6, right? We're basically going to do the same exact thing up top. So from here, I'm going to have equal to x times x minus 2 minus x minus 2 over x minus 2. So I just brought everything to the same denominator. And now if you compute all of this, you get x minus x plus 2 over x minus 2. This goes away, and I get the same solution from the start. It's nothing like it's not rocket science or anything like that. It's basically just like a computation trick. But why should I care about it? Well, if I apply the same thing here, in my case, that's the only reason I care for. Because if I apply the same thing in my case, I can write this fraction as minus integral of 1 x minus k minus 1 over x dx. That's the whole idea here. And why are these fractions nice? Well, because we know what the integral of each of those fractions is. So just to continue the work, integral of 1 x minus k minus 1 over x dx is equal to integral 1 x minus k dx minus integral 1 over x dx. And if you didn't like the trick or anything like that, you can disregard that. What's more important is that you know what these integrals are. So my claim is that this is just ln of x minus k. This is just ln of x. And I just have a constant at the end. Okay, since I'm going to assume x positive, since I don't want to put the absolute value thing, I don't want to bother with that. Okay. So now as you can see, it kind of gets a little bit complicated. We're actually keeping track of what we have to do, but we managed to compute this thing. And I know it's equal to this t plus a constant. So now I just gotta rearrange it. And I'm going to have, let's see, 1 over r. There was a minus in front, so I have ln of x minus ln of x minus k is equal to t plus a constant. And now from here, unfortunately, you're not done. You need to give me x of t equals to something. That's when you can write x of t is equal to something, then you're done. And just moving this thing on the other side is not enough. I need the right-hand side only to depend on t, no x's on the right-hand side, right? So the proof here, like the actual math, gets a little bit ugly quite fast. And that's why I think I emphasized even in the first seminar, in the first plenary, which I held, I remember, I think so. that you need to get quite comfortable with logarithms and ln, just because in separable, and I made the argument last time, when you're dealing with separable equations, there is a high chance that your integrals are going to be an ln. And you need to be able to work with ln. So I'm going to write again the formulas that I'm using. Here, I know that ln of a minus ln of b is ln of a over b. That's what I'm going to use there. And I'm going to get 1 over r, ln of x minus k is equal to t plus a constant. Now I'll move the r on the other side. And I'm going to get ln x minus k is equal to t r plus just a constant. And again, the same idea comes in. If I want to raise everything to the power of e, the correct way of doing it is e to the ln of x minus k is equal to e to the tr plus a constant, not, no, this is good. This is bad. This bad. Okay? Like there's a difference here. Yeah. I agree, but the constant can be any number, so I multiply any number with any number, I still get any number. Great comment. I should have just written c times r here, but I told you that constant plus a constant times another constant doesn't matter. So I just chose to write constant, it doesn't matter. Yeah.
This is the same hold for when you multiplied by k on the left-hand side?
Yeah. So the problem tells me that r and k are constants. So if I multiply like the integral, the c, this is the constant I got from integration. If I multiply that constant from integration with any other constant, I can just write a c. Realistically, I guess I can keep it c times r, but there's just no point. Right? Because any number, if I'm telling you that c is any number in the world, if you multiply it by r, it's still any number in the world. Right? So that doesn't change. Now from here, the property that I'm using is e to the ln of x is equal to x. So x minus k, and this is getting quite annoying. This is the same thing, e tr, and I'll put times a constant just because again the logic is that e tr plus a constant is equal to e tr times e to a constant. This again is just another constant. So whenever you're dealing with the constant from integration in differential equations, if it's multiplied by a constant, it's still a constant. If it's raised to the power square root, doesn't matter. The constant, you can just ignore anything that's going on with the constant. Okay? Now, how do we actually solve this? Quite hard. I don't know. I have some ideas, I guess. So, I can just write it as x over x minus k is equal to e tr times a constant over 1. And I don't know exactly what it's called, but the product of the opposites has to be equal. I don't know exactly how you learned it, but x is equal to e tr times a constant x minus k. And finally, I can see a solution from here. I kind of lost faith at some point, not gonna lie. X is equal to e tr times a constant times x minus e tr times a constant times k. I even forgot what I wanted to say. Okay, so now I just move x on the other side. Okay, and this is just equal to, now I finally got the answer, which we're done. Okay, now we can see exactly why it's called an exponential growth, because you have e to the power of t times the constant. So at each time, at each period of time, this grows exponentially, right? Exponential growth. I don't know how many of you have done the Solo model, but basically it's kind of the same equation. It's not really the same equation, but it's the same concept. Now, any questions on what I did here? I think, this is an example where the actual, sorry for that, the actual integration was, I guess, not as difficult if you knew the trick, but let's pretend the actual integration was not that difficult. I think what was actually the hardest part was after doing the integration, dealing with all that ln and just getting this clean x of t from stuff like this, right? That's what I think the hardest part in this example was. And there's no way to tell where the difficult part arises from. The only thing you could tell basically when you write the f of t and g of x is, the only thing I could tell is that this right-hand side is going to be very easy to solve. That's the only thing I could tell, which I took full advantage of. Now, what's the time like? Let's see. Do you have any questions in particular on this that I solved, or separable or differential equations? Because I think then my next plan is, so I'm not going to give an example here where we're just saying, oh, solve the particular for x of 1 is equal to some number, just because I don't want to deal with all of that. So, and I don't think there's much educational value. But if there are no questions, I think the next step that we are doing is just taking some exam problems really and see where we're at with the exam problems. So, yeah, let's see. I think so just gonna give you some ideas. There's gonna be at least one problem. I would say exactly one problem, but I might be wrong, of differential equations integrals from the exam. I think usually have 4 problems. One of them is differential equations, something like that. Usually problem 2. So let's actually look. We're gonna do it the old classic way. Math 2 UIO. And I mean, unless you have a year you want to try, where is it? Examination. What? No. I think 2018 was something I wanted to try. Wait, they don't have the problems here?
Go back. Then you scroll down. Then it will be there somewhere. Yeah, there.
Oh, yes, finally. Okay, we're good. Exam. We're gonna use the guidelines if we get stuck. Hopefully that would be quite embarrassing, but hopefully that's not gonna happen. Okay, so why is it in Norwegian? Anyway, so as I said, problem number 2 is gonna be what I more or less taught. And as you can see in this case, we have some limits, which I'm not really planning on solving right now, but if you want, you can do them. We're only going to focus on problem C, and that's all. Okay. So I'm going to assume that you've thought or you've tried problem A and B. And here's the main trick that you have to remember on the exam. Even if you haven't solved part B, let's assume I haven't solved it, okay? It was too hard for me. I can still use the result from problem B on problem C. And that's extremely impactful. Let me give you an example. Oh my God. How do you shut this shit down? Okay. So the problem asks me to find the general whatever for x0e, sure. I didn't quite copy the thing. So problem number C from, I don't know, 2, that's 2018. And it was x dot is equal to x times 1 minus ln of x e to the power of t ln of, what is that? Okay, I am starting to think this is not a good idea. This looks very ugly. It would be quite embarrassing if I actually failed this exam, right? Okay, so you get this ugly formula that's telling you to find the general solution for 0e. And you have to do this, okay? Now, remember what I told you, if the problem is usually ugly, that's usually a good sign. If it's very ugly, it's a good sign. If it's very nice and short, it's a bad sign because it means it's very hard to solve. But if it's ugly, it usually means you can kind of solve it. Now, let's see exactly what I mean by that. So let's be honest here. Looking at this, I kind of don't really have a lot of ideas on how to solve. Okay. But I have this, I know that if I attempt to solve it, the standard method is I just look for constant solutions. I identify first and then see where I get, right? So my first step, I know that this looks like a separable differential equation, and that looks something like f of t g of x. So my first step is just to identify what I can do. Okay. And after thinking a little bit, so okay, by the way, here's the, I'm gonna do this one, and then the next problem, you choose the year, you're gonna do yourselves. So now I'm just gonna identify, and f of t, this thing has t over here, this apparently only has t, and this thing only has x, right? That's my observation. So identification seems to be kind of all right. G of x is equal to x1 minus ln of x. F of t is equal to e t ln 1 plus e t squared, some very ugly stuff. Right, everyone on board with the identification? Makes sense? Basically everything that has t on one side, everything that has x on the other side. Now my next step is I'm going to look for a constant solution. Constant solution is basically g of x being equal to 0, which means x1 minus ln of x is equal to 0. When I multiply two numbers and they're equal to 0, one of them has to be 0. That's the main idea. So I'm either getting x is equal to 0 or 1 minus ln of x is equal to 0. So, ln of x is equal to 1, so x is just equal to e. Now, are these solutions? They normally would be, yes. But the person that made the problem wanted to trick us because they said right here, x is in 0e, open. So x cannot be 0 or e. Okay? So my answer here would be because x is in 0e, no solution. in this case. Right, makes sense. Open means I'm not gonna get my edges. Like X can't be the edges. If it was like this, if it was a closed interval like this, then I would have had two solutions. But since it's open, I have 0. Now, unfortunately, we're getting to the step that we've been avoiding, which is actually computing the differential equation. So I remembered that 1 over g of x dx is equal to integral of et ln of 1 plus et squared. This is bad. D of t. All right. Oh, sorry. I replaced one, but not the other. Anyway, this was f of t, and g of x is I'm gonna replace it. It's just x 1 minus ln of x dx is equal to integral et ln of 1 plus et, some squared here, dt. All right, and we get this, and it looks absolutely horrendous. Like I'm not gonna lie, it doesn't look too good. So before panicking, I would suggest just looking at, especially if you're on point C, looking at what point B tells you. What does point B tell me? Well, point B just tells me, again, this is point B, and I can't emphasize this enough. Even if you have not solved B, you can still use B. So I've not solved B. I'm not that good. But problem B basically just tells me that, what is it? Problem B tells me that the first derivative, that the first integral x1 from u 1 minus ln of u du is equal to this ln of 1 minus ln of x, which is whatever. And then the other one tells me that a half of integral of, what's the v? E of v ln of 1 plus ev would have made it a little bit less obvious, really, but is equal to this ugly formula which we don't actually care about. All right, so I basically just copied what point B tells me. That's all I did. I copied what point B tells me. And now I would hope that you see why I care about point B. All right, why do I care about point B? Well, point B gives me the solution to the first integral, like, right? Can you see like that it's basically the same integral, right? And it also gives me the solution to the second integral. I don't have a black pen, but they are literally the same. They're basically giving me the solutions to that thing. So all that I'm going to do is I'm just going to say, if I was in an exam from here, I would just say using B, even if I left B completely empty, or I even drew something nice there instead of actually solving them, I would just say using B, I get ln of 1 minus ln of x is equal to 1 plus e to the power of t, ln of 1 e to the power of t minus 1 plus a constant. And now the only thing I have left to do, which is a little bit of computation, I agree, it is a little bit of computation, is just pull this ln x out. Sure. Great question. So that is, so, okay. So the answer is yes, it is quite different when it's a definite thing. And realistically, if you wanted to convince yourself fully, you would just have to take a derivative of this and show that it's equal to that. If you want it to be completely thorough, I'm pretty sure there's a minus here, but anyway, the main point stands that they are giving you the solution to what you need to solve. If the integral seems completely unsolvable or something, then you either missed out on the identification, or you didn't just look at point B or A or whatever it is, right? Because in this case, all they have to do is just do some ln work and I can get X out of here. And I basically didn't solve anything. And I think in terms of actually the points, it was the pointing, I think, was split. I think, I wasn't here back then, but if it's the standard, then it would probably be like 5, 10, 10. So this is like 10 points really of work, right? We're basically just not doing much. But yeah, I think we're gonna take a break and then you're gonna choose which problem you want to solve. We're gonna choose an exam and you're gonna solve that problem. All right, let's go back. So one thing since we were close to the break, I just wanted to like wrap things up, basically showing you that there's no computation here. But just to be a little bit thorough right now, there are two things I want to add. So the first one, which should be quite obvious, is a half of this integral is equal to this, right? So the whole integral is just equal to 2 times this. That's just a fast change, right? If a half of this is equal to this, then the full thing is equal to 2 times this, right? That's just not, it was just a 2 question. And now I got this interesting question in the start, at the end of the lecture is, sure, this is an indefinite integral, and by definition, integral of small f of x dx is equal to big f of x plus a constant, right? That's the definition. And the property is that the derivative of big f of x derivative with respect to x is small f of x. So using the second one is straightforward and makes perfect sense. The first one, since it's definite, it's a little bit more, I mean, it's not really more complicated, but we got to be careful in the sense that integral from a to b of f of x dx is equal to f of b minus f of a. So it's a little bit more complicated. But when you're given something like this, even with a definite integral, you have to think that this is a prime candidate for the solution, for the antiderivative. You have to think that maybe even if I had indefinite here, that would be the answer, right? Like so I know that the integral from x equals 1 of 1u 1 minus ln of u du is equal to ln of 1 minus ln of x. I would be interested what the indefinite integral is. What is this equal to? Again, the only change is that it's indefinite. There are no heads of integration. So that's why my question is, what is this? And you have to think that maybe, ideally, I'm dreaming, maybe it's just ln 1 minus ln of u plus a constant, right? Maybe it's just like the same thing. You got to think of that. And the only way you check this is basically just by taking the derivative of the right-hand side and seeing if it's equal to what you want it to be equal. So I'm just going to take the derivative of ln 1 minus ln of u, derivative of u, and see what this is equal to. If I'm correct, then it should be equal to this thing. If I'm wrong, then it's kind of messed up. But if I'm correct, then I'm done. This, if you take derivative, is just, using the formula f of g of u, derivative of u is just f prime g of u times g prime of u. So this is just 1 over 1 minus ln of u times, I'll write it in steps. Okay. So the derivative of ln 1 minus ln of u, derivative of u is equal to 1 minus over 1 minus ln of u times, what's that derivative? It's minus 1 u. All right, this derivative is this. Sorry about that. So this is just equal to 1 minus ln of u times u with a minus in front. So did I get the same answer? Did I get exactly what I was hoping for? Well, almost. Almost. There's this minus in front. So how do I correct this minus? I just put a minus here. Minus here makes plus. Right? And that's why before we left class, even though we were kind of rushing, even though we were rushing, I did put the minus in front because I saw that ahead of time. Okay, I put the minus in front. I copied the same exact thing, but I put a minus in front. This is something a little bit technical, but you got to be careful. They might try to trick you with, like, this 1/2 in front, so you forget to put the 2 here, or this definite integral, so you forget the minus. These are like small changes. So in the end, even if you forget them, you would still only lose like a couple of points, not that many. All right, it would it would more or less probably be attributed to computation mistake. But if you understand what I said, or if you have any questions, ideally you don't lose any points along the way, especially what I would call these being easy points, right? 3 points there, 2 points there, 1 point there, it adds up. Now, any questions on this one? Now, am I done? Well, I gotta just take ln of x out of here, but I think you guys have seen enough ln and exponential work for now, and I would much rather have you guys do a problem. So, have you chosen a year that you want to do? I would not recommend, I think, 2020. I don't think 2020 is a good year. But any other year, if you want, I don't know, you choose. Any suggestions? I'll help you out, I promise, after you work on it. All right, let's see then. Kind of skimmed over them, but here, so we did, is this 2019? I think so. No, that's 2000. Let's look 2019 then. This actually looks kind of nice. Yeah, I think let's do this one. This is fine. Let's just focus on B. We're just gonna do B, and then if you guys want, we can do C or A if you guys feel like you want to do it. But in terms of differential equations, we're only gonna do B. So I'll just zoom in, and it's 25 past, so let's just go until 30 past. And you should be, I think you should be quite able to do this. I'm not expecting really in 5 minutes to actually get me the answer here for the constant, but at least get the general solution, or at least get close to it, or or at least go on the track of getting it. All right, I think those are 5 minutes. So how do we do it? Well, let's see. So, I wrote the differential equation. I kind of looked for a second at it, and it seems like it's a clear example of a separable, right? Just because I know x dot is equal to gx times f of t, and this only t, so this is my f of t, and this only x, this is g of x. I would hope this is at least what, or at least what you guys saw. I hope. Now, the first step is to see if they're constant solutions. That means g of x is equal to 0. If g of x is equal to 0, I have e to the x minus 1 over e to the x is equal to 0. For this to be equal to 0, I need the top part to be equal to 0. So e to the x minus 1 over e is equal to 0. So e to the x is equal to 1 over e, which is just e minus 1. So I got x of t is equal to minus 1. For all constant solution means it doesn't depend on t. X is just minus 1 for all t's. And that includes x minus 2. So in particular, x minus 2 is equal to minus 1. So I've solved the first part. This constant solution, x of t is just equal to minus 1, constant because it doesn't depend on t, solves the first pinpoint. So not bad. I got 5 out of 10. Now for the other 5, I have to do the general solution, which is just integral 1 gx dx is equal to integral f of t dt. Plug in the numbers, and I get, this is actually, I was expecting it to be nicer. I get 1 over e to the x minus 1 over e to the x. Sure. Okay. Dx is equal to integral t e minus t over 2 d of t. All right, this step should have been fine for everyone. Now, use point A. Point A literally just tells me that integral from t to e minus t over 2 d of t is equal to c minus 2, I don't know, it's just an ugly formula there, t plus 2 e t over 2. So literally point A gives me the solution to this. All right, that's the trick. I copied it here. Literally the solution to the right integral, which in my opinion looks the ugliest, I immediately just got the answer for. So I'm doing quite well. The only thing I have left to compute is this. So let's see if we can do something here. So I have integral 1 e minus x 1 over e minus x dx. I've made the argument before that I hate 1 over 1, like too many overs. So I'm gonna move this e to the x up top, right? Because 1 over x is equal to x. So I'm just gonna move that on top, and I have integral of e to the x minus 1 e dx. And I am okay. I don't know really what to do here, but I have an idea, I guess. I don't know if it's the correct one. We'll see. I'm just gonna write integral ex, and I'm gonna do minus 1 over e plus 1 over e. That's my idea. I hope we all agree that this is just 0, right? Like it makes sense for everyone. If I add 1 over e and I subtract 1 over e, if I give you a banana and then I take a banana away from you, you have 0 bananas, right? So this is just zero. So basically, it's the same equation. But now, why did I write it like this? Because I'm thinking of splitting it. And I'll split it EX 1 over E, EX minus 1 over E, plus 1 over E, EX minus 1 over E. Everything dx. I just split the numerator into two. Why did I choose this split? Is because this becomes a very nice one. So what I'm left to solve is integral of 1 dx, which is easy, plus integral of 1 over E this way. So this on the right hand side is just x. And now, again, same argument. I hate 1 over 1 over 1 over things. So I'm just going to multiply everything by E. And I'm going to get 1 over E x plus 1 minus 1 dx. And now the problem is basically over. Because is it? Oh, I did some poor math mistake here. What? Give me 1 second. A typo somewhere. Wait. I think I have some, but I have a typo somewhere which I missed. I mean, that's yeah. I don't know why I did this. I have anyway. I have a typo from somewhere here, which I can't seem to see right now. But let me show you. Let me show you another proof. I just wanted to give you like a more intuitive one. But let me show you another one. I can't seem to find the typo right now. So happens to the best of us. Sometimes you get a typo, sometimes you're lost. All that's important is that you have different ideas on how to solve it. So first of all, you should do a lot of integrals, or you should do a lot of derivatives. Both of them work, because realistically, just looking at this, yes.
Could you just do substitution if u equals dx minus 1 for e?
Yeah, I don't. Okay, so you can do that, but my argument was that I don't even think I need to really. So what I meant is, I don't think I was here on this exam, but I've seen people after doing a lot of exercises, and even myself, you can just tell what this integral is. Any ideas of what it is, just looking at it. What does it look like? Any ideas? So I can probably write it down, but so whenever you have 1 over an f of x, it's usually a great idea to think of that f of x as being ln of something. So I'm just going to try my dorky idea, which is I'm just going to try ln ex minus 1 over e. I have no idea if it works, but it's usually a great idea to try that. So I'm just going to try it. In the sense that derivative, am I right or am I wrong? right? It just works out. Again, use the formula f g of x. Derivative of x is just f prime g of x times g prime of x. This is g prime of x. This is f prime of things. So I haven't even thought really of a proof. What I tried doing last on the previous page was just some intuitive stuff. It didn't work out. Then I just looked at it and I tried the second version. Now, there was a suggestion from the public in which they were like, okay, just try the substitution. Sure, you can try the substitution, but you're gonna do, I guess, so many integrals at some point, which I know the classes phase wrong weirdly. I was hoping that while I'm teaching integrals, you are actually doing integrals, but that's not the case. You will eventually just see them. Like realistically, if on the exam from here, I would just see this, I would be like, sure, makes perfect sense. Okay. But since we're still here, I guess we could do the substitution method. I guess, right? You just do e of x is equal to u. And then you have d of x times derivative e of x is equal to u. So d of x times e to the x is equal to u. This is the substitution method. And if I were just to replace my thing, I would have ex minus 1 over e dx is equal to integral, and I'm going to write like this, ex dx over ex minus 1 over e dx. Why did I write it like this? Because I wanted to emphasize what? That dx ex is equal to u, and ex, oh, it's du, sorry about that, and ex is equal to, I missed the d here, du. Okay. I just wanted to highlight the fact that ex times dx is equal to du, and ex is equal to u. So in the end, you're stuck with integral of du over u minus 1e. No du because I already wrote it. And this is now clearly ln of u minus e plus a constant, I guess, if you want to put it, but not necessary. And now I just got to replace this with ex. So I have ln of ex minus 1e plus a constant. Again, this is a necessary proof, I guess, but I mean, I wouldn't call it necessary proof. Realistically, on the exam, if you would just see that this is the thing, and then maybe just write the derivative just to prove me right, prove me wrong, or prove me right, that would be more than enough. So you don't need to do substitution. If you have this thing of like actually seeing it, seeing the integrals or the derivatives, I don't need to see all the proof realistically. Now, if you're gonna argue that, if you're gonna tell me that you magically saw, let me give you an example. Where is it? If you magically saw the previous exercise we did, if you're gonna tell me that you magically saw this integral over here, you just magically saw it and you didn't need to do any computation, you just know that's the answer, then I might call BS on that. I'm gonna say no, I don't believe you, right? But these type, when you have 1 over f, they usually are ln and they're quite very intuitive after some point. But for these ugly big integrals, you have to show me the work on the exam, because if you just tell me the answer, I'm not going to believe that you can just feel the integrals like that. Anyway, now let's finish our problem. So our problem was here. This was our problem. And now we've computed, what is this? Not good. And we've computed everything. So I know this term is ln of e to the x minus 1 over e. And I know the right-hand side is just this from point A. From point A, c minus 2 t plus 2 e t over 2. And now, unfortunately, for all of us, we gotta raise the power of e. So I get e to the ln of ex minus 1 over e. Again, it's e to the c minus 2 plus t. Stuff like that. So I just get e to the x minus 1 over e to c minus 2t plus 2. Again, the formula that I use here is e to the x, e to the ln of x is equal to x. That's the formula that I used. And e to the x is equal to 1 over e plus e to this ugly thing, which I'm not touching just because I have no interest in making it look nicer. It doesn't help me. And now finally, to make everything look nice, I'm gonna take an ln of this. The reason is ln e to the x is equal to x by definition. So I get x of t is equal to ln e plus e to some constant to t plus 2 t over 2. And I know it looks ugly, but I don't care. It can look however ugly I need to look. I'm done. For me, the problem is over, right? It doesn't matter if it's ugly or not. One thing that I wanted to emphasize is this constant, carrying the constant correctly with you, right? I've seen some lazy work, which sometimes works, but sometimes it has nothing to do with the correct answer, in which they just do all the work with no constant. So they just pretend the constant isn't there. And when they're done, they just say, oh, plus a constant here. And that's wrong. Obviously, this constant here is gonna be different than this constant here, right? So that's why it's important to just keep the constant. Now, just to finish our problem, they were asking us x of minus 2 has to be equal to 1. Plug in t is equal to minus 2, x is equal to 1. So yeah, this is the moment where you just whip out your calculators and do it. But it's, you know, I think I can do it by hand. So I'm going to replace t with minus 2 and t here with minus 2. And I know 1 is ln of e. So this is just e is equal to 1 over e plus e to the constant. Why? Because if I plug in t minus 2 here, I get minus 2 plus 2, which is 0. So this whole thing is 0. And I'm left with this. So the constant is e. Okay, let's write it nice. The constant is just e minus 1 over e. So the constant is just ln of this thing. Now, could you have done this on a calculator? Sure. If you're really fast and you are fast on a calculator, which is a skill I don't have, I would have wasted much more time plugging in the numbers and computing everything here, rather than just observing these things. But again, it's personal preferences. If you get here, if you have time, and if you're I don't know, if you're more confident in a calculator, you could have just plugged in everything here and computed. So that's up to you. Yeah.
Just about constant.
Sure.
You've said that sometimes it's unnecessary to include the constant and sometimes it's necessary. Do you have a good way of determining when when it's important to include the constant?
Sorry, did I actually say that you don't care about a constant or you drop it, or what do you mean by it's unnecessary?
Yeah, like for example, when you do by parts.
Oh,
Or,
sure.
I think you mentioned it.
Sure. Yeah. No, so the argument was the following. Let me explain. Yeah, I know exactly what you I think I know exactly what you meant. So when I'm writing this, I can actually write it again. So when I'm writing integral of 1 gx dx is equal to integral f of t dt, right? When I'm writing this thing over here, there's no point in putting a constant for each of the integrals. Let's say I solved it and I get h of x plus constant 1 is equal to big F of t plus constant 2, right? If I just were to put a constant for each integral I solve. Just so we're clear, this is equal to this is equal to that. Okay? In this case, I would just move the constant on the other side and I would get h of x is equal to f of t plus constant 2 minus constant 1. So that's why I'm saying there's no point in putting constant on both the integrals. It's important that I put it on one. Because instead of this, I can just write constant. So I don't know, let's take a simple example. Integral, I'm just showing the concept, I'm just gonna take literally the simplest integral I can think of. Okay? This looks pretty basic. So I'm gonna solve this and I'm gonna put both the constants and see if there's any change. So this is ln of x plus constant 1 is equal to t plus constant 2. And then I can write ln of x is equal to t plus constant 2 minus constant 1. And my point was that instead of writing this, I could have just, from here, I could have just said, I'm not going to put a constant on the first one, and I'm going to put a constant on the second one. Right, like that's my point, that I don't need these things. I can just have this. That's why I say that I can drop a constant from one side because I'm going to have a constant on the other side.
So as long as you include the constant on
one side, it's fine. And like again, you can realistically, for if you're scared you're gonna forget, you can just write it like this. That's perfectly fine. But you know, if you have two integrals, you're gonna end up with three constants, so it's gonna get uglier and uglier. Just remember to, when you get something like this, just replace it with another constant. And then if I would get c minus another c3, I can just put another constant. So it's all about creating a habit which you are comfortable with. If you're just comfortable with writing the constant every time and just basically, you know, changing them once you get to c2 minus c1 or something like that, then do that. If you're comfortable that you will not forget the constant and you will always put it on at least one side, then just do it on one side. I'm just saying it's not necessary to put it, and this is like a simple proof for it. Well, we kind of have 5 minutes, so I would rather just end it here unless you guys have questions for me. But yeah, these were all my lectures. You're gonna have Niels next week, probably starting differential equations. So no, differential equations. So I wish you the best of luck, guys.